Hey guys, it's Professor Dave. Let's discuss polysaccharides.
He knows a lot about the science stuff. Professor Dave explains.
Carbohydrates include simple sugars like monosaccharides, but they also include polysaccharides, which are long polymers of these simple sugars. So we need to understand the way they polymerize as well as certain characteristics of the resulting polymers. First, let's return to our Haworth projection for beta-glucose. In the cyclic form, we can see there is a hemiacetal group, and if we remember the mechanism by which a hemiacetal will become an acetal, that is essentially what will happen here. We know that if this hydroxyl is protonated, it could leave, and then this carbon could be attacked by an alcohol, forming what we call a glycosidic bond, as well as an acetal functional group in the process. But if the alcohol that attacks is one of the hydroxyl groups on another monosaccharide, we will get a disaccharide. This is still an acetal functional group, but it links two monosaccharides together via a glycosidic bond. Here we have a beta-glucose linked with another beta-glucose, which makes cellobiose. Other common disaccharides are lactose, which is beta-galactose and alpha-glucose, and sucrose, or table sugar, which is alpha-glucose and beta-fructose. We could continue to polymerize further, making an oligosaccharide, which will have 3 to 10 saccharide units, or a polysaccharide. Polysaccharides can have thousands of monomeric units, and nature uses these quite frequently. For example, cellulose, which is abundant in plants, consists entirely of beta-glucose units connected via 1,4 glycosidic bonds. This means that carbon 1, the anomeric carbon of one sugar, is connected to the hydroxyl on carbon 4 of another sugar, and it will extend in beta fashion from the anomeric carbon. This pattern can extend indefinitely, with beta-glucose monomers connected in this way. Starch, which is abundant in potatoes and rice, is another polysaccharide made from glucose, and it only differs from cellulose in that all the glycosidic linkages are alpha instead of beta. This one difference in stereochemistry gives the molecule different properties. In addition, starch is comprised of amylose, starch molecules that are linear, and amylopectin, which is the same as amylose, except it has branching every 20 to 25 glucose units. The branching will occur between carbon 6 of one glucose and carbon 1 of another, and another chain initiates from there. Similar to amylopectin is glycogen, which also has alpha-1,4 linkages between glucose molecules, but glycogen has even more branching, occurring every 10 to 12 glucose units. Glycogen is an important way that we humans store energy inside our cells, and enzymes will break down some of this glycogen into individual glucose molecules in times of strenuous activity or in between meals, while other enzymes can add glucose units back to the chain to store them for later. So we now have a clearer picture of what carbohydrates are, from simple sugars like monosaccharides and disaccharides to huge polysaccharides with thousands of repeating units. These will come back later when we learn about cellular respiration. But for now, let's move on to another type of biomolecule, lipids. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.